So we start with a blank Google window as usual, but we've also got this notepad. It's the site notepad.js.org. I love taking notes here. There's no ads. It's nice. So I've got some of my Google searches pre-stored here. The first one I'm going to run is how do I plot a histogram for my quantum computer program in Qiskit? Let's just ask the AI. So before we dive too much into this, we're going to catch up to where we were in the last video in Google Colab. And we're going to create a new notebook. And then we're going to pop open the IBM Qiskit documentation. And just as before, we'll go to Qiskit SDK, Python, and click the QuantumCircuit model. I'll put this link in the description. And we copy the code from here into our Google Colab notebook. Now, if you remember, we do need to install a couple things with pip install, namely Qiskit itself and pylatexenc in order to draw the circuit. Then we also modified our circuit so that instead of having 3 qubits, it has only 2 qubits. Because we now only have 2 qubits, this third qubit, which is at index 2, 0 indexed, is no longer needed. Instead of creating a GAZ state, we're creating a Bell state with the 2 qubits at indexes 0 and 1. Let's go ahead and run it and make sure that that works. And while that installs and initializes, we'll take a look at some of the code that we have here from the AI query on how to plot a histogram. So the first thing that we'll notice is that it says QC equals QuantumCircuit, where our code says circ equals QuantumCircuit. That's arbitrary. It's just a variable name. We could call it whatever we want. We'll stick with circ. More importantly, ours just takes one argument in its constructor. So if you only pass one single number into QuantumCircuit, in this case 2, then that means how many qubits we have. But you can also pass a second number into it, which we see here, 2, 2. And then in that case, the second number is how many classical bits we have. 2 qubits, 2 classical bits. The reason we want the 2 classical bits is because once we look in that box, that cat's either going to be dead or it's going to be alive. It is not going to be in some ghoulish in-between state of dead and alive. So it's either a 1 or a 0 when we measure it, and all we need to store a 1 or a 0 reliably is a classical bit. So it's better to use a classical bit to store the results. Meanwhile, we can check to see that the program worked and it drew our circuit diagram. Okay, so after we initialize the quantum circuit, the next 2 lines are essentially the same. We have .h and .cx. So it passes index 0 for the qubit it wants to put in superposition with a Hadamard gate or an H gate. And then it uses the CX gate to entangle that with another qubit. So then we have 2 qubits. They can either both be 1 or they can both be 0, but they can't be some mix of the two because we're using the entangled qubit as a control on the controlled knot, and it's already in superposition before it's used as the control, so it's not going to know whether or not to trigger the knot operation until one of the qubits is measured. It triggers the knot operation if it's a 1, it doesn't trigger it if it's a 0, and so they're always going to be the same, either both 1s or both 0s, and that's called a Bell state. So we create the Bell state with our 2 lines of code, .h, .cx, and then we have this new line of code, .measure. We see from the comment that it measures qubits 0 and 1 into classical bits 0 and 1. So let's examine carefully what exactly that looks like. It means that we take qubit 0 here, and we put the result into classical bit 0 here. And we take qubit 1 here, and we put its result into classical bit 1 here. And we execute that measure operation on our circuit called circ. The next thing it says is choose a backend, and execute the circuit with this aer.getBackend. Now here's a can of worms. This particular Google query copies code from an older version of Qiskit, and it'll admit that if we copy the aer.getBackend, we can ask Google itself, is aer.getBackend deprecated in Qiskit? Deprecated is a fancy word for old and useless. If we ask Google, it'll say, yes, aer.getBackend in Qiskit is deprecated. Okay, well that's great. Thanks for telling me that. Well, what's the command now? Well, it's okay. Starting with Qiskit 1, it's deprecated. So, what version of Qiskit are we using? I can see here where it downloaded it that we're using 2.1.2, but it's tricky because if I tell it that I want the commands for 2.1.2, the AI hasn't yet picked up on that version. It's so brand spanking new. We got to ask it, what is the latest version of Qiskit? Oh, all-knowing Google AI. And it'll tell us the latest version is actually 2.1.1. So that's the version we're going to ask it about. And we're going to ask it basically the same question. How do I plot a histogram for my quantum computer program in Qiskit 2.1.1, not just any version of Qiskit? And now we see some more useful code. From Qiskit AER, import AerSimulator. This is the newer version. So we're going to copy these imports that we don't already have. We already have the QuantumCircuit. But below that, we're going to add these two new lines of imports. And of course, we get the squiggly underline under Qiskit AER, which tells it that it doesn't know what the heck Qiskit AER is until we do a pip install Qiskit AER. These lines of code are the same. Define a quantum circuit with 2 quantum and 2 classical bits. Create a superposition. Entangle it with another bit. And measure both bits into classical bits. And then here is the code to run it on a simulator. We see it says shots equals 1024. What? Is this college? Nobody's doing 1,024 shots. What are you talking about? It's basically the number of executions. Like I said earlier, we're going to run it 1,024 times in order to get a good spread of data on it. And we're not going to get counts on QC because our circuit is named circ. Same thing here, squiggly underline, rename it to circ, which is our circuit. And after it runs 1,024 times, it stores the results in this variable called result, and then gets the counts out of result and puts it in a variable called counts. And then finally, plot histogram counts. This title is optional. It'll give the bar chart a title. It's a nice touch. Let's go ahead and run it and see if it works. One thing to note here is that we're using two different draw methods. We're using plot histogram here, and then we're also using circ.draw. And we're using them one after the other, and that can actually confuse it. That's why it didn't draw the histogram. So there's a couple ways around that. We can forego drawing the circuit and then see if it plots the histogram. There's another trick that we can use, which is to use IPython.display. So there's our histogram. We see the 0 zeros won out. Anybody who's betting on green in roulette will be thrilled. 534 0 zeros to only 491 ones. But I'd like to be able to see the circuit too. and it didn't draw the histogram if it drew the circuit. So I did some more Google searches. I said, hey, I found this library called IPython.display. It says that explicitly using it achieves the same results if you use display fig, where it says fig equals plot histogram counts and display the plot histogram. Sometimes I had to also use the word explicitly here, which in computer lingo basically means do it exactly how I tell you and don't think for yourself, oh computer. But we can copy this code, and this particular snippet didn't have our fancy title, so we're going to actually give it the argument that includes the fancy title. So our figure is a plot histogram of the counts with the fancy title, and then it's going to display the figure. Like this, display. And with this display keyword, it is explicitly calling this method called IPython.display. So we can also import it from IPython.display, import display. And we don't need to pip install it because IPython it's part of the Python language. So it knows what that means. It means really, no, really, I really want you to display it. Okay, let's try it. So using this display keyboard, we can draw both the circuit and the histogram. Ooh, dill. I didn't know this came with dill. Numpy. Oh, here it is. Okay. So again, the double zeros went out in our Bell state measurement results, but it's a different number every time, right? It's probabilistic. This time we have 530 double O's and 494 double ones. We don't have any O1s or 10s, right? Because those are impossible in the Bell state. Let's try it again and see how the probabilities change. Now, it's August 2025 when I'm making this, and as of only very recently, it is possible to get free runtime on real quantum computers. So at some point in the future of this video series, we're going to actually run code on real quantum computers. When we do that, we're going to see a small error graph in the histogram plots under 0, 1, and 1, 0, just because barking dogs and happy couples and laughing grandmas and cosmic rays cause heat and disturbance in the pristine quantum computer system that jostles the little qubits and causes them to error out some small percentage of the time. That's part of the reason why we draw these histograms. And another part of the reason is because even in a perfect execution, the entangled and superposition states, really any state that's in superposition, whether it's entangled or not, has this Schrodinger's cat-like, dice with the universe-like property to it that it's really only meaningful if you measure it statistically. A single run has too much chance involved. So that's a histogram of our Bell state. In the next episode, we're going to play around with the circuit, take it beyond a simple Bell state, add extra qubits, add qubits that aren't entangled in combination with qubits that are entangled in the same circuit, and take a look at how that affects both the labels on the bars and the magnitudes of the bars themselves. Thanks for tuning in. This has been QuantumEasy. I look forward to seeing you soon again.